Okay guys, welcome back. So in the last video I talked to you about the how we can apply the conservation of energy for problems in gravity, and what is the minimum velocity that should at which an object should be projected from the earth or from any other planet or any other surface, so that the object gets rid of the gravitational attraction or the gravitational field. And I call that velocity to be the escape velocity. So as I mentioned in the last video, I'll be talking about the motion of planets and satellites, the time period, the revolution, and the other concepts in this video. So to begin that, I'll take a simple example, right? So consider a satellite of mass m moving around a planet of mass capital M in a circular orbit radius r, right? So this is the thing what I'm going to do, right? Now I'll take a satellite of mass m. I'll take the satellite to be like this. Right? The satellite to be like this, and the earth to be like this. So the planet's mass is m. Right? Planet's mass is m, and the mass of the satellite is simple m, and the radius of this, that is the distance from the center of the earth or center of the planet to the satellite is, I'll take it as simple r. Alright, so the distance is simple r. So if you take the orbital velocity to be v naught, orbital velocity means, now this is actually going in an orbit, right? This is actually going in an orbit like this, right? I actually can't draw the whole part. Now it's actually, orbit means actually a circular, I think it's elliptical, right? Or circular elliptical, it's an orbit. You know the concept of orbits, right? So it will go in an orbit. So the orbital velocity is v naught. I'll take at this point is v naught, right? So what you can say is that this orbital velocity of this object. Now what are the forces? First of all, what are the forces acting on this object? The first force acting on this object is the force of attraction, right? Force of attraction. For the force of attraction, you can write an equation, right? So the force of attraction is equal to, from the Newton's law of universal gravitation, equal to g, which is the universal gravitational constant, times the mass, the product of the mass of these two objects, divided by the square of the distance between these two objects. So that is r squared. So F equals g capital M simple M by r squared for this problem. And this force should be, now if this force, only this force was present, this object would get attracted, and due to this force this object will move towards this object, right? This is a case like as if we are dropping an object, dropping a ball, right? Dropping a ball from outer space, say from about say 10 meters high, right? So I'll take a distance 10 meters high from the earth's surface and I'll drop a ball. So that is similar to the concept as mentioned here. So what actually happens is that the satellite is not coming towards the earth, satellite is moving around the earth. So for the satellite to move around the earth, this force which is the force of attraction due to the earth's gravitational field should be cancelled out by an equal force, but opposite in direction and linear, right? So that is actually from the Newton's third law. So some other force should be acting so as to cancel out this force. So if this mass is moving with velocity, what actually happens is that this object now according to from the rotational motion, this object has the centripetal force, right? The centripetal force. So the centripetal force acting on this object should be equal to the force of attraction in order for this object to remain in this place. So if you write for the centripetal attraction, you can say F equals m times the square of the velocity of the object. So the velocity of the object is equal to the orbital velocity divided by the distance between these two objects. So actually the Earth is acting like a fixed point. Now this is very similar to circular motion. So the Earth's center is acting like a fixed point, right, relative to this object. So the distance between these two objects is r, right? So if I take this to be equation 1 and this to be equation 2, you can equate these two, 1 and 2, because the left hand sides are equal, 1 and 2. So what you can say is that the right hand side should also be equal. So g times capital M times simple M divided by r square is equal to m times v naught square divided by r. So m is not equal to 0, r is not equal to 0, so one m will be cancelled and one r will be also cancelled. So v square is equal to gm by r. So v is equal to now root gm by r. Now there may be some problems in which the mass of the satellite, mass of the Earth is not given, as well as the value of g is not given. So in that case, now you know from the first video on the series of videos on gravitation, I explained to you that gm by r squared is actually equal to the gravitational acceleration, g, right? Gm by r squared is equal to g. So you can take this to be gm by r times 1 upon r equals g, right? What I did was I split r squared into 1r and multiplied by 1 upon r, right? So this is the quantity we are actually concerned about. That's why I split that. This is the quantity gm by, we are not concerned about gm by r square. We are concerned only about gm by r. So this is the quantity we are concerned about. So that is equal to, if you cross multiply, that is equal to gr. So gm by r is equal to gr, right? Equal to gr. You can substitute gr in place of gm by r here. So v is equal to g times r. So v is equal to g times r. So this is another equation. So both of these are equal. So if the mass of the Earth is not given, or mass of any planet, right, not the Earth, any planet is not given and the value of g is not given, you can simply find the velocity from this equation as well. So that is about the motion of planets and satellites. Now if you substitute the value of r here for the Earth, you will approximately get the value of v. Actually this is v naught, right? This is not v naught. Value of v naught to be approximately, right? Approximately 8 kilometers per second. Kilometers per second, or 8,000 meters per second. Alright, so that is about the motion of planets, right? Motion of planets and objects around some fixed point. Now what about the time period of revolution of these objects? Alright, the time period of revolution of these objects. Now you know that if now you have heard about simple pendulums, about circular motion and the other concepts, even in, I think it's in waves also, right? So in many concepts you have heard about how to get the time period for not about an object under gravitation, about an object in circular motion, or in pendulum, or that's also a kind of rotational motion, and in waves and so on. So the time period of revolution for a particular object is the ratio of 2 phi against the angular velocity. So t is equal to 2 phi by omega. So that's actually a popular equation you may have not memorized by now. T equals 2 phi by omega, right? So this is the equation you know by now. Now we are not being, if we were not being given the value of omega, we have to find that. But now the velocity, now under gravity, this object, the angular velocity is actually equal to the ratio of the translation velocity against the value of the radius. So v equals r omega, right? You can say v equals r omega, right? So you can substitute that, you can not substitute, you can say that omega is equal to v by r. Omega equals v by r. Now this is like purely going through the circular motion. So you can substitute the value of omega v by r here. So t equals 2 phi by v by r. So that is equal to 2 phi r by v, right? 2 phi r by v. So actually you can also put S equals ut for this, right? S equals ut plus half ut squared. So the value of S will be 2 phi r and the value of t will be S by u, so that will be 2 phi r by v. So that's also equal to this one. So what actually happens is that we already found the value of v to be gm by r, the root of that, right? So I'll substitute that here. So t equals, now you know that v equals root of gm by r, so that I proved little while ago. In this same video. So I can substitute the value here. So t equals 2 phi r by root of gm by r, right? So what I'll do is I'll square this term. So t squared is equal to now 2 phi r squared is 4 phi squared r squared. So that will be 4 phi squared r squared divided by the square of gm divided by r is gm by r. So I squared this term because in order to get a simpler equation, because there is a root inside, right? So the square of the root will be the power to 1, because root is half powered, and when you take the square that will be power to 1. So anything to be power to 1 is equal to that. So that will be gm by r. So you can simplify this to like this. So t squared is equal to 4 times phi squared times r squared, and this r, now this r will climb up to this portion, right? You know from the ratios. So that will be r cube divided by g times m. So actually now this is a constant. You can also simplify this to be t squared is equal to 4 phi squared by g times r cube by m, right? What I put it right? R cube by m. So actually the value of t square is the value of t square is directly proportional to the cube of the radius and is inversely proportional to its mass. So when the mass of an object, when the mass of the planet or mass of the object in which the other object is rotating decreases, the value of t increases. So when the radius increases, when the cube of the radius increases, the value of t increases. So actually you have to take the value of this one. So 4 phi squared divided by g is a constant. You can actually find that. So if you are solving one or two equations with this, right? One or two equations with this, what you can actually do is that you can solve the value for 4 phi squared divided by g, and then you can find the value t squared equals some constant times r cube by m, and then you can solve it. So this is the concept of time period of revolution, and in the first part of this video I talked about the motion of objects and satellites. So this is just another video on the series of videos on gravity. So in the next video I'll be talking about a new concept, but that is also on the gravity, right? Okay, so I'll be talking about that in the next video, and see you then.